Apparently Hamilton used to be bigger than Florence. Long time ago.
Wow. Superbubble is pretty big now.
Very huge thing. It's just small. There are actually people who live in Hamilton that commute. Because commuting from Hamilton is more infrastructure. At North Toronto, it's harder to get downtown.
Oh, because of the subroad.
They pushed up housing prices.
Oh, yeah.
Yeah. Well, we own a house, so I don't know how many people we live in. The general question.
Right.
But we used to be able to tell just by the fact that, hey, how cheap. Not as true anymore.
It's kind of like the same everywhere.
Yeah. Australia's getting expensive in my opinion. My parents sold their house 15 years ago. Way too much money. Moved back to Tasmania. Tasmania's still so much. It's not a go-to destination.
It's small.
Yeah, it's still pretty rural. Fun to visit. I don't know if kids find it really boring.
The weather was quite different, right?
Yeah, it's quite simple.
Like most of the time.
Yeah, like it's a nice place to excel.
Yeah, it's
Or
rural.
maybe a bit before this.
Paddle around the river.
I did see rain.
Look at sheep.
See it happen.
Oh, there. Seems like it's wrong. Could be a little not wrong.
So we do start at 6 months.
You have to upgrade. Yes, there's nothing rain. It's cold, but it's not too bad. The temperature is actually. It's the one. Right one to us.
Yeah, I think there's a sure.
I know it's ridiculous.
Sounds good.
Go to the whole string.
Thanks. Alright, this will also be off.
Tomorrow's actually.
Okay.
All right, welcome. So today we have the honor of having James Wadsley here. So James is from Australia and moved to Canada for his grad work at the University of Toronto. After this, he moved to Seattle, working with Craig Hogan and the N-Body shop there. And that's also where he wrote the gasoline smooth particle hydrodynamics code. So since then, he's been involved with a number of computational projects and public open source code. So he's now a professor at McMaster in Canada for the past 15 or 20 years, I think. So thank you for coming, and we're going to hear about both galaxy evolution and maybe a little bit about planets
Planets at lunch. Planets make better lunch fare, I think. So I wasn't quite sure what the audience was. So if something seems interesting, you should perk up, and then I will spend longer on that slide. But otherwise, it is a mix of what I do. And so I like to start with this. Phil Hopkins makes gorgeous movies. But I think everyone in this room at least is aware that having a pretty movie doesn't necessarily indicate physical correctness. And many of us in this building also are somewhat interested in what goes under the hood in a galaxy simulation. And this is old woodcut I really like, of the guy poking his head behind the curtain of night and says, wow, what's going on there? So the components that go into simulations include a collisionless component, dark matter, typically modeled by particles, which might include be modeled by a tree code or something like that. Hydrodynamics, nominally Euler's equations, but I think you can argue that there's variations on that we occasionally have non-trivial mean free paths, we have turbulence, we have other things that modify the simplest assumptions there. Radiative cooling, which gives you interesting equations of state, effective equations of state, but also a very large amount of small scale physics, stars, black holes, things like this. And typically a fairly simple prescription for how stars are formed, or any dense structure would be formed. And those stars also feed back on the gas to restructure it and limit the star formation. I think there was kind of a lot of back and forth on hydrodynamics for many years. But I think recently there's actually been pretty good convergence on hydrodynamics so I feel like it's actually a smaller contributor to uncertainty between groups now. As you can see, back in the past, SBH, I think it's fair to say, did have significant issues, but that dates back to sort of 2002 or so. And one day, Volker may actually update Gadget. But I think he's far more invested in a repo these days, so it's low on his priority list. But when it comes to galaxies, the big thing I think where a lot of people are focusing their attention is what is driving the energy input, what is structuring the galaxies, what is holding them up, what is redistributing the material in them, what is driving the formation of dense phases that might lead to star formation. And we have a very large number of potential drivers here. The galactic scale drivers, energy drivers, you would hope you get for free. You get them from, you put in a good gravity solver, a good hydrodynamic solver, you have decent resolution, you just get that kind of thing for free. Galaxies naturally accrete, and that's fine. The stellar component, however, is largely unresolved. So you have to introduce some subgrid model to handle that, and there's a very large number of components. And there's also sort of secondary effects, X-rays, UV backgrounds, things like this. They're kind of an external input to some degree. And there's a lot of interest in AGN at the moment as a potential driver of structure and formation and evolution of galaxies. For me, I know there are braver people than me in this room, but I think that one of the issues with this is that if you get Tiziana's movie and fast forward it a little bit, then what is a very gentle looking evolution becomes quite, if it wants to keep going on me, becomes quite violent towards the end. And so I think you can sort of see it starting to cook nicely here, and then essentially this is a very early AGN model, completely blew these galaxies apart, right? Completely destroyed them. This is, as I said, very early model. The resolution is sort of tiny. It is not great, sorry. It's a sort of 0.1, 0.2 kiloparsec level. And you can contrast that with recent work by Talbot et al. Using a repo. And in this case, even when they orient the AGN, so the jet is within the disk of the galaxy, as you can see in the diagram shown here, it did not destroy the disk, right? So I feel, as I said, there's a brave subset of people who are willing to do AGN feedback, but I feel that it's too hard to constrain, right? So you can certainly put it in and you can parameterize it, but how exactly to do that is hard. It's very resolution dependent. So I'm not going to focus on AGN feedback. The simulated view of galaxies is a little different to the observational view, and simulators, when they go to conferences with no observers, will show things like this that they often wouldn't show to observers, and that is the temperature density phase space. So we can see kind of the whole galaxy laid out here, plus a bunch of IGM as well around that galaxy, with temperature vertically and log density on the x-axis. And we have sort of the reddish color here shows your typical ISM sitting around 10,000 Kelvin. We have a cooler phase. I think most simulators would recognize that cooler phase is probably not quite at the right temperature, but dynamically it's not well supported. It's making a colder, denser phase, which we then nominate as the star forming phase, right? And a lot of our ideas about how to do this, how to do star formation and feedback, date back to the time when this diagram was essentially cut off at 1 atom per cc, right? And now we're progressing into these denser phases. We have more resolution, and a lot of the models we use haven't really caught up with that to reflect the better resolution. And so this is a somewhat arbitrary division by me of this space into what this material reflects. So the top part of the diagram is sort of hot collisional stuff. This is the halo, the gaseous halo, but it also includes outflows, hot inflows, but also remnants. So some of that material, people just dismiss it and say it's out there in the middle of the CGM or something, but there is actually material in the disk of the galaxy, in remnants, in supernova remnants, etc., that has these conditions. It has densities down to 10 to the minus 3, temperatures of 10 to the 7 and above, and so there's not a one-to-one spatial mapping here, whereas people tend to dismiss that and say, well, that's accreting stuff, that's CGM stuff, don't worry about it. And then you have the IGM, Lyman Alpha Forest. This is cold material, up to about 10 to the 5 K, ultimately maybe incorporated into galaxies. You have the CGM, which is material, hotter material flowing onto galaxies, potentially that accreted hot collisional material now cooling, joining the disk. You have the ISM, the classic ISM. It's got a WIM, it's got a warm neutral medium, a cold neutral medium, etc. So that's kind of marked in red here, around 1 atom per cc, and this is sort of probably the best observed phase of these. A lot of the other phases like CGM are tricky. You have to look at them with quasar absorption lines or something like that. It's a kind of indirect measurement. And then you have the molecular phases, which we would love to get as simulators, but I feel is very hard, just from a resolution perspective. So my talk, I'm actually building up to my outline of the talk. I want to argue to you that a really big contributor to the hot collisional component that has been somewhat neglected is still supernovae. Like, we always thought supernovae played a role, but I would argue it plays a bigger role than people often assume. So that's point one. And if you're doing it right, there's actually a large chunk of this plot which should be empty. You shouldn't be putting material in this region of the plot, and yet a lot of simulations do. And then there's another region, which is the IGM, which is sort of the classic UV background, uniform radiation field part that I feel that we've been doing quite well at as simulators. But a lot of the other ones, I feel like you really need radiative transfer to do these well, because they're close enough to the galaxy that the galaxy itself could be the primary source of radiation for this material. So just assuming some kind of uniform background is going to be wrong, essentially, maybe by orders of magnitude in terms of the radiation field that this material experiences. So my second point, or second aspect of the talk is, I think we need to do more radiative transfer. I know Aaron would not disagree with this, if we want to get these phases right. So the overview of my talk, I was going to joke that this is my early conclusions, is that superbubble feedback is very important. Many simulations still miss key aspects of supernovae, and that the total gas content of galaxies is critically dependent on this. I'd certainly agree that if you go to larger galaxies, AGN and other physics will definitely play a role. So I'm not claiming that supernova can do everything, but I think they're critically important, particularly for smaller galaxies. And I think a lot of people have gone wrong in trying to do overkill on their feedback to sort of compensate for missing key aspects of how supernovae work. And the other thing I'd like to argue is that gas phases are an important diagnostic, and I think just getting the stellar mass of a galaxy right is actually not sufficient to claim you're doing everything well. And I think that radiative transfer is going to be a key part of that. And yes, it's expensive. So yeah, I understand why people aren't always doing it. So to take a step back again, I'm essentially arguing that stars play a big role here. And this is the budget of energy output from stars. It's done in a per stellar mass way. And so it's an average star cluster. And so if you have of order 10 to the 6 solar mass large star clusters, it's a reasonable thing to do. Most of the energy is coming out as light, right? And a small fraction is coming out as winds and supernovae. It is quite interesting that the rate for both the winds and supernovae is quite comparable. So you can kind of lob those together, and in the early days of superbubble research, actually, they were lumped together, that winds cleanly segue into supernovae in terms of what they do in the galaxy. But what I would like to do is to sort of break this down. So even though you go down 2 or 3 orders of magnitude when you look at winds and supernovae, they are qualitatively different. They create much more energetic feedback, and they push you to a qualitatively different regime, which I will call a large-scale regime. Whereas when you look at a lot of the other feedbacks, they're definitely important on the scale of within the ISM, within a GMC, but they have a kind of intrinsic upper limit because a supernova can get material up to 10 to the 8 Kelvin. 10 to the 8 Kelvin corresponds to 1,000 kilometers per second. It's an interesting speed on the scale of a whole galaxy. Whereas a radiation feedback generally can't get you much more than 10,000 Kelvin, which is 10 kilometers per second. It's not an interesting speed on the scale of a whole galaxy, definitely an important speed within the ISM, within a GMC. So I would say there's a scale separation between these feedbacks and what you can expect from them. And one of the reasons that scale separation exists and is so clean is because of the cooling curve, right? So if you push stuff up to 10 to the 6 Kelvin, the cooling curve drops off steeply there, and it can stay there for a long time. So if you can push things into that regime, then you have very effective feedback that can do a lot on the scale of your galaxy. If you only push up to 10 to the 5 Kelvin, then the cooling curve just steals that energy straight back down again. So this is why I would argue there's actually a very natural, this is not an arbitrary separation, there's a natural barrier that makes these two very distinct kinds of feedback. So superbubble feedback, star clusters. So the key insight that led us to think about superbubble feedback was the fact that stars form in clusters, which hasn't been assumed in simulations actually in general. And part of the reason was, of course, resolution used to be bad. When your star particle is 10 to the 6 solar masses, it doesn't even make sense to talk about clustered feedback. However, as our resolution is improving, and many people are now in sort of the 100 solar mass, 1,000 solar mass regime, then clustering that feedback and treating that correctly becomes important. And this is an image of a superbubble within the LMC. Image is about 100 parsecs across. So these things are quite large, so eventually should be resolvable structures in our simulations. So even a 10,000 solar mass star cluster should generate 100 supernovae. So you have a lot of input to blow up this bubble. It's not a single supernova. Single supernovae, I would argue, are not very interesting. You have to cluster them to get something interesting. There are a lot of fun classical models for supernovae. I actually got invited to a retrospective conference from McRae based on working on superbubbles. Apparently he used to be superbubble guy, and then he became Supernova 1987A guy and stopped doing that. But he did a lot of really important early work. And the key thing is, these were first developed as a model for winds, stellar winds, but you can apply supernovae to this context just as well. The idea is you kind of draw a loose barrier around the star cluster itself and say, I have mechanical input. It's stellar winds, it's supernovae, and I'm going to treat it as though it's continuous, which average over time it is. Now, in the details, there is some intermittency, but you can think of it as an averaged input steadily occurring over about 40 meg years. That input inflates the bubble, and it's a little different to what we would assume compared to, say, a Sedov-Taylor single supernova blast. In particular, you end up with this pressure-driven snowplow type solution, and you have quite a lot of energy staying within the bubble. And the reason is thermal conduction. So thermal conduction actually is attempting to transport energy out of the bubble, but what it does is it lifts the inner layer off the cold shell instead. So it basically only dumps energy into material that is entering the bubble. So almost all the kinetic energy in the bubble actually stays in the bubble, about 45% of the original injection. A small amount is lost in the shell. You're pushing that shell that's sweeping material up, so about 35% is lost, and about 20% is in the form of kinetic energy of the expanding shell. If you compare this to what's often assumed for individual supernovae, they assume that on a timescale of, say, 10,000 years, you're losing 90% of the energy. So this is a very different context, and it relies on including physics that is often missing, such as that thermal conduction. Right? So this is why I would argue not a lot of people are doing this, because they're not doing the physics you need to do. The hot bubble mass is also self-regulating. So the thermal conduction, because it's so sensitive to temperature, it only really gets large when the temperature of the superbubble exceeds about 2 million degrees. So 2 million degrees or so, the conduction rate goes up. And you start mass loading the bubble until you bring it down to about 1 to 2 million degrees again. So that means there's a natural attractor for how much mass loading you get and how much ejector you should associate with superbubble. And that's what's kind of cool, because a lot of other work, they have a certain resolution, they dump the supernova into that, and therefore your ejector has the mass of whatever resolution element you just dumped all that into. Here you have a natural process that determines the ejector mass. It's strongly correlated with the energy that you've injected, right? So this is one reason why I really like the superbubble model, because it has this attractor that takes you to a certain answer that isn't dependent on your numerical assumptions.
Question.
Sure.
So some superbubbles may originate from hypernova or
Gamma
Yeah,
rays,
definitely, yes.
And are these much less numerous, or if you take the mass function of stars?
I couldn't say, I don't have a number in my head for the frequency of hypernovas and so on, but within the sort of basic Weaver, the 77 framework, any kind of energy injection should give you a similar outcome. As long as it thermalizes in a shock
Right.
on a relatively short distance scale, it should just behave like a mechanical energy input. So I think you could just lump in other sources of energy into the same framework and it would be fine. Sure.
Yeah, so you talk about thermal conduction.
Yes.
Do you use Spitzer conduction or?
We have a modified Spitzer conduction. So we tend to take the Spitzer conduction as an upper limit, and we assume that it will be somewhat limited by tangled magnetic fields or other physics.
Okay, and it doesn't make a big difference?
No, because it's such a strong attractor to this behavior, we can vary the coefficient by a factor of 10, and it doesn't really change behavior. Yeah. So to make this model work, my former student Ben Keller, who's now in Tennessee, at Memphis, we put this in, so we need the conduction. And I do understand why people don't want conduction, because it's a diffusive process, it has grotesque time step limitations, and so we're paying a price for that. We're working on trying to limit that. I have a student working on how to improve that. But yes, so it's not free, I think is the short answer there. Also, the scale of the evaporation fronts on the inner edge of that bubble is a fraction of a parsec. So we cannot resolve them. So we had to put in an explicit model based on McLaurin-McRae for the evaporation.
what is the mean free path of protons or
Electrons. So I don't have a number for the ISM. I know in galaxy clusters it can be of the order several kiloparsecs.
Tens of kiloparsecs,
Yes.
actually.
Yes. So on this scale, I think it's of the order of tens of parsecs, if I remember
But
correctly.
that's the size of what's the size of your bubble?
100 parsecs up to a kiloparsec.
You're not worried about the mean free path being large?
Well, as I mentioned, people often invoke, so real superbubbles are slightly smaller than the Weaver prediction, and one of the things that's invoked is tangled magnetic fields limiting the mean free paths, for example. So yeah, there's definitely an uncertainty there on what the exact mean free paths are. So we put this, oh, is this not playing? It seems to have frozen. Oh, there we go. I will wait. So this movie is just meant to demonstrate what's going on. The bottom line is that it's a Milky Way, so it's not very exciting. It's mostly doing fountains, it's not doing big outflows. But the key thing is I am generating gas above 10 to the 7 Kelvin, which isn't a typical outcome for these kinds of simulations. Could make a choice here. Thank you, Microsoft. Could take several minutes. All right. Maybe I should skip that movie.
There's some major outage in Microsoft.
Right now? Right. So that's what the galaxies look like. I will skip past the movie. The key thing being that I was making 10 to the 7 Kelvin gas, and so that means that that hot region shown in my phase diagram here actually includes material that is still within the disk of the galaxy. It is not accreting material, it's not CGM, it's actually the top right, the highest entropy part here is actually still within the disk of the galaxy. And that's one reason why it was critical to have two-phase particles. If you just get a simulation and you shove a lot of temperature into your ISM gas at 1 or 10 or whatever atoms per cc, the entropy is actually not that high. And so if you compare that to the entropy of the halo, it's less, and so you cannot be buoyant within the halo. However, if you have multi-phase particles, you can actually get a correct supernova remnant density, or order 10 to the minus 3, and then the entropy is extremely high. And this material can essentially buoyantly compete with material in the CGM of the galaxy. So the red line is supposed to show what's going on. We instantaneously create material in our ISM that has a very high entropy, and we essentially jump right over this short cooling time block of material in the right of the diagram. And this is why simulators don't often show these diagrams. So I'm not going to name names, but there's a phase diagram from the literature in the top left where there's a whole bunch of stuff at 10 to the 5 Kelvin. And this was a strategy which is still quite common, to just turn off cooling in your feedback regions. It's like, I cool too much, I don't like it, I'll turn it off. And then there's another one in the bottom, which is an effective equation of state model. So it's like, my ISM is not behaving itself, I'm going to impose an effective equation of state that I like, that supports the galaxy in the way I like, and that's what's going on in the other one. So you can see that the effective pressure of the dense medium is extremely high to support the galaxy at the scale height that they wanted. So one thing we really like about the superbubble is we kind of get this structure naturally without having to kind of impose parameters. There's another thing here which I kind of like. My collaborators often tell me off for showing this slide, but I love it. Which is that simulators have a tendency to get the answer they want, right? And if they don't get the answer they want, then they don't show it. And there was a fun project in 2012 with Cecilia Skinner-Pierco. This was right at the time when abundance matching of galaxies was coming in. So no one knew what the correct stellar mass to halo mass numbers were when the project started, and they all naively submitted their simulations. And then when the paper came out, they started to know, and so they could put the simulations on the diagram on the left. And you can see the vast majority of them are converting far too much gas into stars, right? The only ones that didn't were ones that had, they knew something was coming and had started to put fairly extreme feedback in to compensate with that. But all the codes had some trouble, and we had trouble too where the yellow cross in this, and so we were also in trouble. But it's fun because it's an interesting insight into the intuition or lack thereof of simulators. And so we pursued this with Superbubble to try and see what would happen, and the galaxy as it looks at redshift 0 is shown in the bottom panel. So we have a no feedback galaxy which doesn't have much gas left, a blast wave galaxy which was using an older feedback model, and a superbubble galaxy. And the blast wave model has a big bulge, and the superbubble models don't have much of a bulge, and they have quite a lot of feedback at the end. And we did try superbubble ×2, and many of you probably know this is a common game to play in simulations. You say, well, my feedback's not quite working, maybe I'm wrong, maybe the IMF's a bit weird. I'll multiply by 2 or 3. TNG did 3. And it's a trick, and you say, well, maybe there's hypernovae, or maybe somehow some of the radiation output from galaxies from stars gets converted to help support my feedback or something, and then I do a multiplier. So we did that as a backup plan, but it turns out we didn't need it. We got good rotation curves on the same objects just fine using the Superbubble. Whereas the previous versions of this galaxy had crazy rotation curves because they had excessive bulges. And we got a pretty good halo mass to stellar mass, or stellar mass to halo mass ratio. This is just one galaxy, so it's sort of moving stochastically around the average behavior. But it turned out that just a normal supernova ejector did very well at the end, redshift 0, and excessive ×2 actually was a bit low at the end. So we're pretty happy that supernova model with Superbubble do quite well, and there's even room for reduced efficiency. So if you want to introduce mean free path problems or something else that's extracting energy from your superbubbles, we have room to do that. So we're pretty happy about that. And the other interesting thing is that high redshift outflows are key. So a superbubble that gets you to a few million degrees can only push an outflow of order a few hundred kilometers per second, and so it's not going to get you out of very large galaxies necessarily, right? So it means that we have to control the baryon content of galaxies early when they're dwarf galaxies. We cannot kick baryons out of low redshift galaxies. That doesn't work. And so essentially we get a huge fraction of the baryon content of galaxies and push it into the CGM, the far CGM, where the time to fall back again is on the scale of many gigayears. So whether it's unbound or just on a very slow train to the IGM doesn't really matter. It's not going to come back on a reasonable time scale. And so that's reflected in the diagrams shown in the middle, primarily that the outflow rate is quite high at early times for the superbubble models. Can supernova do it all? I love this work by Mike Hudson. He's Canadian, and so they actually used weak lensing to measure the stellar mass to halo mass directly by stacking many, many images to get a signal. And they show that the efficiency of star formation dramatically declines once you get much larger than Milky Way mass. And so that's okay, because that's roughly where we expect AGN to kick in. So the brave among you who want to do AGN feedback models, we need you. We need you above 10 to the 12 solar masses, because otherwise the galaxies don't work. And we tried this ourselves, and yes, it doesn't work. So in a model with superbubble only, we could get good halos up to about 10 to the 12 solar masses, and then beyond that, no, they started to fail, and essentially they just couldn't kick matter out anymore. The superbubble kind of has this upper limit where it's not very effective once the potential is very, very deep, essentially. And we're quite happy to say use AGN or something there. But it was really quite an interesting, sharp transition that we saw in our data.
I have another question.
Sure.
So, I think I followed everything. You keep talking about the superbubble model.
Yes.
Is that still a subgrid prescription, or is
It's
it
a subgrid
that
prescription.
you're resolving the whole star cluster?
So in terms of raw physics that we've introduced, the main one is conduction. But beyond that, much of it has to be subgrid. We cannot resolve the bubble wall, etc. So that part is subgrid.
So what does that mean? You just keep injecting some energy?
We inject energy, but every cell or particle in the simulation is two-phase. It has a hot phase and a cool phase. So we explicitly model a hot interior and a shell within particles experiencing feedback.
Okay.
And you allow the dark matter to respond?
Yes.
The inner parts of galaxies as
Yes.
well?
So the superbubble is actually quite good at making core dark matter profiles, actually.
That's important.
So one thing that's interesting about superbubbles is they are qualitatively different. A lot of the wind models that people use introduce winds that have very high speeds. 600 to 800 kilometers per second is not uncommon, right? And that's kind of what you have to do. If you want to brute force your way out of a galaxy, you need to inject a lot of energy to create an outflow. However, superbubbles are like a balloon. They don't have to go very fast because their entropy is so high that they're always buoyantly rising. So they can actually bubble their way out of a galaxy at speeds more like 100 kilometers per second and continuously do that. So if you can get your entropy high enough, you can do this. And so if we focus in on the material in the phase diagram that has been touched by superbubbles, that red part is actually still very much within the inner regions of the galaxy, including material within the disk. And then the diagonal line that's labeled 4 is an adiabat. It's just simply moving outwards, lowering its density at constant entropy, right? And so by the time you get to the blue region, you're into the CGM, and potentially you're getting low enough in temperature that you can now cool again and come back into the galaxy. But the whole timescale to do this can be very long. So in that sense, we don't care whether the material has been completely thrown out of the galaxy. It's just been put out there for a sort of a long time, and that's good enough to defer star formation and get the stellar mass to halo mass numbers reasonable, but also to have much of the CGM gas is not very detectable. So you can hide a lot of stuff there and solve a lot of issues in terms of baryon counts. So that's just a diagram showing more or less the same thing. But the good thing is if we compare this to the Cos Halos data set, for example, we get a consistent range of speeds. So the Cos Halos data set seems to imply that the typical speeds of material moving out in the halos is more like 100 to 200 kilometers per second. It is not at the level of, say, the virial velocity or an escape velocity. And so this is very much consistent with a buoyant-driven outflow model versus a sort of a brute force, cold wind, if you like, driven model. So this is just a quick summary. So we like it because we didn't have to invent a lot of numerical parameters. We were lucky in a sense. There's a bit of an attractor here in how it behaves. I think almost all the uncertainties push in the direction of the superbubble being less effective, right? All the sort of real ISM issues would push in that direction. They would have, for example, you can have cooling in the layer between the shell and the hot bubble because you're transitioning through 10 to the 5 Kelvin in that layer, right? So there's processes that might remove energy. So we would argue that the superbubble is actually an upper bound on what supernova can do. But we think it's a relatively clean one because it's not very parameter constrained. We believe supernova are actually more effective than people tend to assume. You don't necessarily need to reach for cosmic rays or AGN or something to get decent galaxies. We certainly agree that you probably need AGN if you want to get decent galaxies above some mass. But we don't think you need to go there, particularly for dwarf galaxies. And I would just say it's a cautionary tale. I know actually there's some early papers with Neil Katz and Lars where they did this, and they just threw in 10 to the 51 ergs per supernova and it didn't work. They said, well, it doesn't work. And so it's funny, we've known this from the start, that you can't just toss the energy in and expect it to work. You have to think a bit harder, and yet we still have people not necessarily doing that. So the next part I wanted to mention was radiation a little bit. This is something that's new for us. So we're trying to do multi-band radiative transfer. And we know there's a lot of different kinds of radiation that affect different zones within your galaxy. So there's the FUV, which is the dominant heater of the ISM. People often ignore that. A lot of cosmological galaxy models are actually using the extragalactic hard UV to heat their ISM, which doesn't make any sense. None of that stuff is getting into the ISM directly. So the FUV should be doing that. But also we want the EUV because it's ionizing a CGM, it's giving us a quasar absorption metal lines, things like that, so we need that. And in principle, even the gas is a source. The hot gas in the halo itself, recombination lines from that gas are also a source of radiation. So it's a very complex problem, obviously. And in principle, we need a pretty detailed spectrum. So the way we pursued this is we actually made a piecewise power law to fit the spectrum. So the spectrum I'm showing here is essentially a fit to the Hart-Maddow type cosmic UV background. We have many bands, and we recognize that there are jumps that occur. There's a jump at 13.6 eV for hydrogen ionization, 24.6 EV for the first helium ionization, and so on. So we allowed for a discontinuity at those points. So when we created our fit, that's how we did it with these 10 bands. We also have stellar clusters. The output from stellar clusters obviously evolves over time, and so each of our stellar clusters doesn't have a consistent spectral output, so we've put that in as well. So when you have a star particle in a simulation, the spectrum that it creates is varying over time. And essentially what's falling off most dramatically is the high energy photon part from those star clusters.
And no dust?
We have dust in the simulation. I think, I don't know if you're alluding to this, but definitely I feel, and Aaron knows this too, is escape fraction from young star clusters. If you're not resolving your GMCs, then there's a lot of suppression potentially. And I leave this to future work to know how to do this right, and I feel it's very hard to constrain. But yes, I would say this is like a naked star cluster with no absorption around it yet. Definitely, yeah, whatever's happening is subgrid, yeah, messy. So this is our Hart-Maddow spectrum, and you can see that it starts fairly sharp with fairly sharp transitions, and then as the population that's driving it, a mix of quasars and smaller galaxies, evolves with Redshift, then the spectral shape is evolving with Redshift, and compared to a piecewise constant fit, the piecewise power law fit that we're using does quite well in reproducing the Hart-Maddow ionization rates, because the ionization rate is really what affects your simulation, right? The gas doesn't care what the radiation spectrum looks like. It cares how many photons are causing ionization. And so we find that the piecewise power law fit we get from our spectrum bands, it does very well for this. And here's some preliminary results. We get really crazy variations in what our spectra look like in different parts. So this is just a random sampling of points within a galaxy simulation. We get very, very large variations. And you can see that the y-axis has a very extreme range. And so many of these spectra are, in practical terms, not doing anything, right? Because anything below -20 here is really zero, essentially. But this is just some raw data from those simulations. We want to do radiative transfer galaxies in cosmology. We have a lot of considerations. We want something that's good for our chemical networks. So with apologies to Aaron, so directionality wasn't so important to us in that sense because we weren't going to do radiation pressure and things like that. We wanted something where we could handle scattering, many sources, and we essentially decided we would assume that the ionization front was the limiting speed, not necessarily the speed of light. So we put all those considerations in, and we decided that we would try a fast ray trace. So it's geometric ray tracing. We don't have an explicit speed of light. It's a reverse ray trace, and so the idea here is you have a piece of your simulation where you want radiation, you trace to it. So that way, if some part of your simulation is quiet on some long time step, you just ignore it. And it's only when a piece of the simulation wants a new updated radiation field, you calculate it then. So in that way, it scales with the active part of your simulation, not the entire simulation. The big downside is we're not doing explicit photon counting. We're not counting every photon and making sure someone gets it. We're actually ray tracing to the receiver in the end. And this, we've called this code Trevor 2. We have a first version called Trevor 1, which we published in 2019. We're trying to get n log n, and that's simply so it doesn't become the dominant cost for our simulations, because n log n is what gravity costs. We want it to cost similar to gravity. The other cute thing we do, which is a bit novel compared to other people here, a lot of people, including Aaron's work and others, are focused on reionization, large volumes. What is the radiation field across a large volume? We wanted to be able to do individual zoomed in galaxies, so we needed a way to approximate the field coming in from the outside on those galaxies. And the way we do that, we put a ring of sources around those galaxies at large distances. As long as that ring is far enough away, if you look at the radiation field in the interior, it's quite smooth, right, in the absence of absorption. So you can actually quite accurately mimic an external radiation field by putting a shell of sources around the zoomed in galaxy. So that's kind of nice. So we can actually do zoomed galaxies with the radiation field, including the external radiation field. So Trevor 2's big bonus is that we now have one tree walk. We used to walk the tree multiple times, which gave us extra log n's in our n log n algorithm. I will say that whenever you do a tree, you have to be a little bit wary. With gravity, for example, gravity goes through everything. There's no equivalent of absorption. So if you just lump all the mass together, you get a very nice approximation of what should happen. If you lump all the sources of radiation together, then it's a bit tricky, because the one on the far side is actually got to go through a lot more absorbers than the one on the near side. So actually collecting together radiation sources into a single unit and doing it that accurately is a pain. And we call this complex sources, and it's something that we're still working on. We have some approximations, but it's definitely difficult. So essentially we're using heel picks. So we only have a finite number of rays coming into each source. There's 48. We can make it more. So that limits our angular resolution in some sense. But we have managed to achieve this n log n. So I have the gravity solver shown here as red crosses, and I have a radiation solver shown as the green dots, and we have managed to achieve an n log n behavior, which means, yes, we're paying more computer time, but it means we can do simulations that we used to do at a fixed resolution at a similar resolution with radiative transfer at a cost that's not sort of ballooning out of control. So that's nice, because simulators hate turning back the resolution and running things at garbage resolution given compared to what they're doing right now. There are tricky issues. Aaron and I were discussing some of these. A major one is that the cells can be highly optically thick. So even at pretty good resolution, such as 10 to the 4 solar masses or better, say even in the Ryan Nebula at 0.01 solar masses, a resolution element could be optically thick. It could have an optical depth of order 1,000 or more. So that means it's actually not very accurate to assume a uniform set of conditions within that cell. There is actually kind of an ionization front at the start of the cell, which is receiving a very high field, and once you get to the end of the cell, you have essentially no radiation left. And so if you just assume averaged values across the cell, you'll get strong systematics. And that's something we've been working to deal with, and so far it's working pretty well, but every time we try a new chess problem, we always find that there's another systematic that comes in. So one of our first applications was to look at galaxies with FUV as a feedback. I mentioned this partly just as advertising, so I know some of you like working on isolated galaxies. And so we've started looking at isolated galaxies, and we have a project called Bespoke. And this goes back to my first comments about using gas phases as a way to really understand whether we're doing galaxies right. I think doing a generic Milky Way-like and claiming everything's good is not as convincing as building a detailed model of a specific galaxy and then seeing if that's good. And our Bespoke project, Alex Pettit is a dynamicist, and so he's built very detailed models of things galaxies, including NGC 5055, 6946, and 7331, including if they have a bar, the bar is there, detailed rotation curve, correct surface densities of stars, gas, and a dark matter halo, all self-consistent and stable. And so what we want to do with that is actually see whether we can reproduce the detailed star formation behavior. Because the Kennicutt-Schmidt is an average over many galaxies. If you look at a single galaxy, it's actually a line in the Kennicutt-Schmidt diagram. So they all have their own twist, and by putting in the detailed dynamics, we hope we can account for that. And so that's a project that we more or less just got started, but I'm kind of interested in talking to people about. The other thing we've been doing is doing cosmological zoom galaxies. This is the 7 dwarf simulation, originally done by Siqing Shen collaborators in 2014. It's got fairly high mass resolution, and we've run it both with Superbubble and Superbubble plus radiative transfer. The movie on the left is Superbubble. You can see there's quite a lot of explosions. The radiative transfer plus Superbubble version is a lot quieter. So the very fast movie on the left is just the radiation field. You can see that it's got a uniform background, and then you have a region around the galaxy within about 10 kiloparsecs where the field is suppressed by the absorption of the galaxy itself. And then right in the star-forming region of this dwarf, within a few kiloparsecs, you have bright regions associated with individual star clusters. So this is an early result from us. And one of the early results that's coming out of this is that the original Superbubble version, which is shown as dashed curves, is quite bursty. So the blue lines here are the H1 content of these galaxies, and so the blue lines are jerking up and down as the Superbubble is creating large explosions of outflows from the dwarf, whereas the RT version is much smoother. It's consuming the gas in a much smoother way, and that's simply because the radiative transfer is a more effective way of regulating star formation, whereas the Superbubble tends to be quite bursty by comparison. So that may have impacts in terms of forming dark matter cores, destroying cusps, things like this. But again, preliminary results, I personally still want to make sure I trust the way that the star formation model and these new models are interacting before I completely trust this result. It also has interesting implications for the phase diagram shown on the left now. So in the Superbubble version, it tends to push to high densities. You have a strong star formation event. It eats all the dense gas and takes it away again, and it happens repeatedly. Whereas with radiative transfer in the right panel, we can maintain a more consistent structure in our ISM as the simulation goes on. So in summary, we have an n log n ray tracer now. We're quite happy with it. It's not perfect, but when compared to a completely uniform radiation background, we think it's a strong improvement. We feel that we need a detailed spectrum. The interest of Siqing Shen and Bernard Baumschlager is very much in the CGM and quasar absorption lines, so we're partly focusing on a method that should be good there. But we also want to develop a set of physically motivated models that will work for not just cosmological but also isolated galaxies, because we feel that isolated galaxies actually provide the best observational inputs to understand the structure of galaxies and the phases of the gas, whereas cosmological stuff is very much in the bathtub thing. You know, as long as you put the right number of baryons in and get the total stellar mass, the halo mass correct, that's usually enough for cosmological people, and the observations don't always constrain the details very well. So our goal is to try and kind of converge and not have two different ways of doing things depending on their target science. So thank you.
All right, do we have any questions to start off?
Sure.
So this is probably going to expose my ignorance here. So superbubbles versus supernovae.
So a superbubble is a collection of supernovae. So
I've seen so many pictures of supernova in this, I can't
Right.
imagine counting them. But superbubbles don't seem to show up, at least in observational form. very frequently. So is there some reason why I'm missing this?
Those holes in the image in the bottom left are superbubbles. So you can see the scale is quite large. These holes here. Right, so individual supernovae are typically not large enough to get to a scale height of a galaxy and thus show up as a distinct hole in a galaxy image. So definitely there's going to be a transition. So you will start with individual supernovae. They will be heavily suppressed by the cloud that they're in, so you probably lose a few. And then after you get to sort of tens or hundreds, you will start to build the bubble. So the bubbles is sort of, it really only gets going when the cloud it formed from is long gone at that point.
Avi?
You didn't want to speak about AGN, but let me ask you, this Superbubble feedback, does it affect the feeding of the black hole?
It does. So I'm collaborating with Ben Keller and Mike Tremmel to try and address that. The first efforts were not good. So yeah, when we just naively included our engine model with our Superbubble model, they did not play nicely together. So yeah, that's a work in progress.
And of course there is this central star cluster in Galaxies, which is far bigger than normal star clusters, so the effect of the Superbubble
Yeah, could be, yes, definitely. My big concern goes back to what I was saying about Rosie Talbot's work with Deborah Siaki and so on, is that I worry about destroying key structures that moderate the feeding of the black hole and so on like that. So until you can resolve that accretion torus and accretion disk, I worry that you're going to need a very big subgrid model. So my distaste for AGN is not so much that we shouldn't have them, it's more that I don't know how to constrain it and build a subgrid model that doesn't have many free parameters. So I'm trying to limit the free parameters I have to deal with at one time.
So related to these superbubbles, so some of the models like Fire, for example, have these like limiting radii for the feedback.
Right.
To kind of, you know.
That's a numerical thing to some extent.
Essentially, you know, get at this without.
Yeah, there are models, right?
Yeah.
So there's this idea that you can measure the effect of momentum injection from a collection of supernovae and do a transition, right? So that you can handle it that way. I must admit, I haven't actually quantified that. It would be quite interesting to look at if there is a significant difference between using a momentum injection versus what superbubbles do. I think the key thing that I like is the way it regulates itself in terms of mass loading and so on.
So do you see like the size of them being regulated at some point? Like, because
there's certainly
these are all
predictions.
kind of similar maximum size, right?
That may be something to do with the distribution of star cluster masses,
Okay.
I think. There's also this effect that once your bubble gets to the scale height, it breaks out and it rapidly loses its pressure. So once the physical size is comparable to the scale height of a galaxy, it tends to kind of self-pop and send a lot of the energy vertically, and that limits how big they can get.
Okay. What do you?
Can you show the slide where you change the Superbubble feedback by factor 2?
That was
Or the maps of the galaxy.
the fluffy galaxy.
Yeah.
It's quite fluffy, yes.
Yeah, so with stronger feedback, the disk becomes bigger, right?
Yes.
You know what's going on there?
Sorry?
What's going on there? Why this?
Well, the images are all stars, so you're looking at the stellar disk. I don't remember the details of this, but I imagine that the stronger superbubble may have suppressed star formation earlier in the dwarfs more, which may mean the galaxy was assembled in a slightly different way.
Oh, okay, so this is cosmological.
Yes, the cosmological simulation.
Interesting.
Yeah, so it's probably buried in the assembly history to some degree.
Sarah?
So is the amount of energy that's injected, does that depend on the size of how large the stars are in the simulation? Or is it
So we have a fixed IMF in that sense. So it's literally per massive star particle. So we assume that the star particle is a totally average stellar population in some sense. And we get the energy injection from that.
Okay, so it's not applicable if the resolution gets...
Yeah, once the resolution's low enough,
to be assumed.
we might need a stochastic component. Ben and I have been talking about this a lot. Is that an important twist on any feedback model, whether it's Superbubble or something else? Should we be taking into account rare events where the IMF is unusual in that particular cluster, for example? Like if you get a couple of really massive stars, it could just completely change the picture. Also, if you get a runaway star, so it does its feedback event outside the core of the GMC, you know, it could change the effective energy injection quite a lot. Yeah, we were thinking, should there be a tail of some kind, right? Should we just be assuming the average, or should we care about these tail events that could have like 10 times the normal impact? Ben has a student work on this, actually.
Okay, final question.
In this figure, did the stronger feedback tilt the galaxy disk, or is that?
This is where I think assembly comes in a bit. So that I think that often the dwarf assembly history is modified somewhat. I also think that we were probably relying on an automated edge-on view generator. So I don't think we can guarantee that it created the same edge-on view in each case.
All right, let's thank the speaker one more time. Yeah, he'll be, I think, around the lunch.
And he's presenting at lunch.
Presenting at lunch? Yeah, I'm going to put my other hat on at lunch.
Thank you, that was beautiful.